Right now, sitting in a peer-reviewed physics journal is an equation that claims the Big Bang didn't need the one ingredient every textbook says it required. Cut that ingredient out entirely, and the universe still expands exactly the way we observe it expanding today. That's not the only paper making a claim like this. Over the past year, 3 separate teams of physicists have each proposed a different mechanism for how our universe actually began, and none of them fully agree with each other. Not fringe researchers, not clickbait. Published, peer-reviewed, competing explanations for the single biggest event in the history of anything. By the end of this video, you'll understand what that missing ingredient actually is, why physicists thought they needed it in the first place, why the last 12 months have quietly become one of the most contested stretches in the history of that theory. Welcome back to Big Data Vault. This is the story of how our universe began, and why the answer you learned in school is no longer the only one on the table. 3 competing theories, published within the last year or so, all trying to answer the same question your high school textbook thought was settled. Hit like if that surprises you, and subscribe, because Big Data Vault covers stories exactly like this the moment they break. Every origin story needs a starting point, and ours starts with a problem that has nothing to do with telescopes. In the early 20th century, physicists working through the mathematics of general relativity kept running into an uncomfortable implication. If you take Einstein's equations and run the universe's expansion backward in time, everything in it, all the galaxies, all the matter, all the energy, gets pushed into an increasingly small, increasingly hot region of space. Keep winding the clock back far enough, and you reach a point where the entire observable universe is compressed into something almost too small to describe. That point is what we now call the Big Bang. Not an explosion happening inside space, the way a bomb detonates inside a room, but an expansion of space itself, stretching apart everything within it. Edwin Hubble's observations in the 1920s, showing that distant galaxies are racing away from us, and that the farther away they are, the faster they recede, gave this idea its first real observational backbone. The universe wasn't static, it was growing. And if it's growing now, it had to have started from somewhere far smaller. Here's the open question worth carrying with you through this entire video. If the universe really did begin from an almost infinitely small, almost infinitely hot state, what actually caused it to expand the way it did? And is the explanation we've settled on the only one that fits the evidence? That question sat quietly unresolved for decades. It's the same question 3 new papers, published within the last year or so, are trying to answer all over again. To understand why any of this needed fixing at all, you have to understand 3 specific cracks that showed up in the simplest version of the Big Bang model. Cracks that showed up decades after the theory was first proposed, and that ultimately forced physicists to invent something new to patch them. By the 1970s, the basic Big Bang picture, a hot, dense universe expanding and cooling ever since, was well supported. But 3 specific measurements didn't fit it, and each one on its own was strange enough to keep a physicist up at night. 2 points on opposite sides of the observable universe have never been close enough to exchange heat. Yet, the cosmic microwave background, the leftover glow from the early universe, reads the same temperature in every direction, to within a few hundred thousandths of a degree. It's like 2 bowls of soup cooked in kitchens on opposite sides of the planet, coming out the exact same temperature, without either chef ever comparing notes. Cosmologists called this the horizon problem. A universe born from a single explosive event should end up curved one way or another, like a sphere or a saddle. Instead, every precision measurement of the cosmos comes back flat to within a fraction of a percent, and even a tiny deviation from flat should have snowballed dramatically over billions of years. That's like balancing a coin on its edge for 13 billion years and having it never once tip over. This is the flatness problem. Every magnet has a north and a south pole, always paired. Particle physics predicted the extreme energies of the newborn universe should have produced isolated magnetic monopoles, a north with no south attached, in huge numbers. We've never found one anywhere in over half a century of looking. That's the monopole problem. 3 separate cracks from 3 separate fields of physics. But that's not even the strange part, because in 1979, one physicist realized all 3 might share the exact same fix. Physicist Alan Guth proposed that in the earliest sliver of a second after the Big Bang, the universe underwent a burst of expansion so extreme it doubled in size roughly 90 times over, all within less than a trillionth of a second. This period became known as cosmic inflation. Here's why that single mechanism cleans up all 3 cracks simultaneously. The horizon problem disappears if the regions we're comparing today were actually in close thermal contact before inflation stretched them impossibly far apart, carrying that shared temperature along for the ride. The flatness problem disappears the same way a wrinkled balloon looks perfectly smooth once you inflate it to the size of a planet. Any curvature gets stretched flat by sheer scale. And the monopole problem disappears if inflation diluted those predicted particles so thoroughly that there's now, on average, less than 1 within our entire observable universe. 3 stubborn problems, 1 elegant fix. For over 40 years, inflation has been the dominant explanation for how our universe got its start, supported by increasingly precise measurements of the cosmic microwave background that match its predictions closely. So here's the real question worth sitting with. If inflation solves the problems this well, why are physicists in 2026 still trying to replace it? The honest answer is that inflation, for all its success, has never been directly detected. It's inferred from its consequences, not observed as a mechanism in its own right. Nobody has ever measured the specific particle, the inflaton, thought to have driven it. That gap has left the door open for competing ideas, and this year, 3 of them walked through it. You'd think that if you wanted to explain inflation, you'd need to invent something new, an exotic particle or field that only existed for that first sliver of a second and then vanished. That's been the standard approach for decades. But a team at the University of Waterloo and the Perimeter Institute, led by physicist Nyayesh Afshordi, published a paper this year arguing something different. Instead of adding a new ingredient to Einstein's equations, they reworked how gravity itself behaves at the most extreme energies in a framework called quadratic quantum gravity. When they ran the numbers, exponential inflation fell out of the math naturally, without needing to invent anything extra at all. Picture the difference between building a new engine to solve a car's power problem versus discovering the stock engine was always capable of that power output, if only you'd tuned it correctly in the first place. That's roughly the shift this paper proposes. And the payoff isn't just theoretical elegance. The model makes a specific testable prediction, a minimum background level of primordial gravitational waves that future instruments should be able to detect, giving this idea a real chance of being confirmed or ruled out, rather than sitting as pure speculation forever. You'd assume that if one team is refining inflation, the next logical step from a rival team would be a slightly different flavor of the same idea. Instead, a team led by Raúl Jiménez at the University of Barcelona, working with researchers at the University of Padua, proposed skipping inflation altogether. In a paper published in the summer of 2025, their model starts from a well-established concept called de Sitter space, which lines up with how we already understand dark energy behaving today, and proposes that gravitational waves, ripples in space-time itself, did the job normally credited to inflation, seeding the uneven clumps of matter that eventually grew into galaxies and cosmic structure. Think of it like 2 competing explanations for why a pond has ripples spreading across its surface. One story says a single enormous rock was thrown in at the very start. The other says the ripples were already part of the water's natural behavior, and no rock was needed at all. Both stories can explain the ripples you see today, but they describe completely different beginnings. The payoff that makes this proposal worth taking seriously is that it's built to be falsifiable, meaning it produces specific predictions that can eventually be checked against real data, rather than being permanently unresolvable. Here's a misconception worth correcting directly. For decades, cosmologists assumed dark matter had to be born cold, meaning slow-moving from the very start, because that assumption is what allowed it to clump together gently and form the gravitational scaffolding that galaxies later grew around. New research from the University of Minnesota and University Paris-Saclay, published in late 2025 and widely reported on in January 2026, challenges that assumption directly. Their calculations show dark matter could have been born moving close to the speed of light, genuinely hot, during a chaotic early period called post-inflationary reheating, and still cooled down fast enough afterward to build the same large-scale structure we observe today. Picture a marathon runner who sprints flat out for the first mile, then settles into the same steady pace as everyone else for the rest of the race. From the finish line, you'd never know they started that differently. That's the core claim here. Dark matter's frantic early behavior might be completely invisible in the calm structure it left behind, which means one of the field's oldest working assumptions may need to be quietly rewritten. None of these three proposals has replaced inflation. None of them is confirmed. All three, published within about a year of each other, represent genuine, peer-reviewed challenges to a piece of the standard story that most documentaries, including plenty of good ones, still present as settled, sit with what it would actually mean if one of these newer models turns out to be right. For over 40 years, the story has been that our universe required something extra to become what it is. A field, an inflaton, a special ingredient that switched on for a fraction of a second, did its job, and then vanished, never to be directly detected. Remove that requirement, the way the quadratic quantum gravity model does, or replace it with gravitational waves the universe was always going to produce anyway, and the entire opening chapter of existence stops being a special event. It becomes the default, not something that had to happen to us, something that was always going to happen to any universe built the way ours is. That's the difference between winning a lottery and simply being handed money you were always owed. One version of our origin story is a staggering coincidence, a single temporary field appearing at exactly the right moment to solve exactly the right three problems, then disappearing without a trace. The other version is almost boring by comparison. Ordinary gravity, behaving the way gravity always behaves, just at energies we've never been able to test directly. If that's the correct account, then the most dramatic event in the history of everything wasn't dramatic at all. It was inevitable. And this isn't sealed off in some untestable corner of theoretical physics. The same uncertainty about the first fraction of a second is already leaking into problems astronomers are fighting over today. The persistent disagreement over how fast the universe is currently expanding, and the James Webb Space Telescope's discovery of galaxies far too massive and structured for how young they are. Both trace back to the same unresolved question. Did that opening moment behave the way the standard model assumes, or not? Here's the honest state of play. Inflation has matched precision measurement after precision measurement for over 40 years. Three separate credible challenges to it were published within about a year of each other, the most recent just months ago. Nobody currently knows which one, if any, is correct. What we do know is that each one makes a real, falsifiable prediction. In primordial gravitational waves, in large-scale structure, in dark matter's earliest behavior, and the instruments capable of testing those predictions are either already running or being built right now. Which means the answer to how our universe began isn't waiting somewhere in the distant future. It's waiting on data that could arrive within your lifetime. Here's the part of this that actually sticks with me. Most of us learned about the Big Bang the same way we learned the boiling point of water, as a fixed fact, delivered once, filed away as finished. Nobody tells you that the specific mechanism behind it, the thing that actually did the work of turning a single dense point into the universe you're sitting in right now, was still being argued over in serious journals within the past year. That's not a small caveat tucked into the footnotes of the theory. It's the beating heart of it, and it's wide open. What strikes me most isn't even which of the three ideas turns out to be right. It's that we're at a genuinely rare point where three teams can look at the exact same evidence, the exact same cosmic microwave background, the exact same expanding galaxies, and walk away with three fundamentally different stories about how it all started, all of them still standing, all of them still testable. That kind of moment doesn't last. Within a decade or two, gravitational wave data will likely rule most of these out, and whichever one survives will get taught the same flat, settled way inflation is taught today, with the doubt quietly edited out of the story. Which means the version of this question you're watching right now, unresolved, contested, actively being fought over, is temporary. Soon enough, it'll just be an answer. So, if you ever wanted to know what it feels like to watch science before it gets decided, this is it. Somewhere right now, someone is running the numbers that will eventually settle how your own existence actually began. If this kind of deep dive into how our universe actually works is something you want more of, make sure you're subscribed, because we're only getting started uncovering what's hiding in the earliest moments of everything. I'll see you in the next one.